Hi, this is Mrs. Bustamante. Today we're going to continue talking about Dalton's law of partial pressures. And we're going to talk about this one because a lot of times this is actually how we see problems or how we collect gases in real life. Oftentimes we have to collect them by passing them through water. So say we'll have some sort of reaction that we do in a closed system. So this one's in a test tube, right, of potassium chlorate, probably heating it up. It's giving off a gas, right? And that gas we're going to use to basically pump through this water system, right, into a place where we can measure how much of that gas we have. Or really, in this case, how much oxygen gas is giving off. And when we collect gases over water, we have the gas in there, but we also have water vapor in that closed system too. So we're going to use that and take that into account when we solve for either the total pressure or really probably just the pressure of an individual gas or gases in there that's kind of unknown. And we can do that because we know that the vapor pressure of water is constant at any given temperature. So we have big charts that will tell us what the water vapor pressure is at given temperatures. Sometimes they come in kilopascals or atmospheres, right? Whatever you need. But we know a lot about water. So we know that the pressure of water vapor is at a certain temperature. And we use that to solve for, say, the unknown gases or gas in a system, right? We also know that the pressure inside of, say, the graduated cylinder or whatever it is that you're collecting this gas in is a combination of water vapor pressure and the pressure of whatever the dry gas is you're trying to pump in there, the unknown gas, right? And the pressure inside the bottle is the same as the pressure outside of the bottle in atmospheres or the pressure of the atmosphere, right? We're not seeing this bottle shrink or expand, so we know their pressures are equal. So some things we have to use and know in order to solve these problems is that the pressure of the bottle is the same as the pressure of the atmosphere. And then the pressure of the bottle is going to be that the bottle feels is going to be made up of the gases inside that bottle, which is the gas that you're looking for, and the pressure due to water vapor. So once we know that, we can solve some problems that look kind of like this. You might say the following gas was collected over water under indicated conditions. Correct each volume to the volume that the dry gas should occupy at the standard pressure and indicated temperature. In this problem, temperature is constant. So they tell me my volume, because here's centimeters cubed, is 3,564 centimeters cubed at 50 degrees Celsius and 159 kilopascals. So some things that I know about this problem, well, first I'm going to have to find the pressure of just the gas. And in order to do that, remember, I have to look up the pressure of water vapor at that temperature. They tell me total pressure here is 159 kilopascals, but I just collected a gas over water. So I have water vapor in there and I have that particular gas. So I'm going to use my chart. I'm going to go over here and I'm going to find the temperature, 50 degrees Celsius, and I see that water vapor has a pressure of 12.3 kilopascals at that temperature. So now I know that the pressure from the water is 12.3 kilopascals and the total pressure is 159 kilopascals. So what's the pressure of just the gas, right? Well, I use Dalton's equation. P total equals the pressure of the gas plus the pressure of the water. And I solve and I get the pressure of the gas is 146.7 kilopascals. But they actually want to know what the volume is at this temperature of the gas. So I'm going to think about what I know. Well, I just solved for the pressure of the gas of 146.7 kilopascals, and they want to know what it would occupy at standard temperature and pressure. And I know that standard pressure is 101.3 kilopascals. And my starting volume, they told me, was 3,564 centimeters cubed. Now, sometimes you ask, well, is that really the volume? Yeah, it is. Even though you have two different substances in there, right? Gases take up all the space. They're spread out evenly. So that is, in fact, the total volume. So I want to know the volume that the gas would take up at this new pressure. Now, this problem told me that temperature was constant, so I don't have to worry about the temperature change. All I'm looking at is my pressure compared to my volume, which means I'm going to use Boyle's law. So P1 times V1 equals P2 times V2. I plug in my information and I solve for V2, which gives me that V2 is 5,161 centimeters cubed. And again, always good to think about it. Well, I lowered my pressure, so would it make sense that my volume would go up? Yes, it would. Now, sometimes you'll get a problem that doesn't say that the temperature is constant. Maybe the temperature changes in the two conditions. What do you do then? Well, instead of using Boyle's law, you would just use the combined law, gas law, that would include your temperature. And they would have to give you a little bit more information, right, in order to do that problem.